Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about covariance functions of random process. The concept of covariance of two random variables can be extended to random process. In previous chapter, we have discussed about covariance of two random variables. So that covariance of two random variables can be extended to random process. So that is here we study. We are going to studying that concept. Covariance indicates measure of interdependence or coherence between two sampled random variables selected from a single random process or from a joint random process. So selected from a single random process which is called as a auto-covariance function, and selected from a joint random process, then it is known as cross-covariance function. Okay, once again the definition of the covariance function. Covariance indicates measure of interdependence or coherence between two sampled random variables selected from a single random process. So selected from a single random process, then it is known as auto-covariance function of the random process, and selected from a two random process, then it is known as cross-covariance function of the random process x of t and y of t. So that is the definition of auto-covariance function of the random process and cross-covariance function of the random process. So mathematically, if x of t comma y of t be joint random process, the covariance of the two sample random variables x of t1 and y of t2 is defined as cxy of t1 comma t2 is equal expectation of x of t1 minus x of t1 bar into y of t2 minus y of t2 bar. Here x of t1 bar is the mean value of the random process x of t, and y of t2 bar is the mean value of the random process y of t. So x of t1 bar is equal expectation of x of t1, which is also denoted as m suffix x of t1. Y of t2 bar is the mean value of the random process y of t, that is expectation of y of t2, which is also denoted as my of t2. So now here there are two time instants. The two time instants are t1 and t2. There are two types of covariance functions, that are auto-covariance function and cross-covariance function. First, we are going to discuss about auto-covariance function random process. When two sample random variables selected from a single random process, the covariance is called as auto-covariance. The auto-covariance indicates a measure of coherence or interdependence between two sample random variables. And what are the two sample random variables from a single random process? The two sample random variables are x of t1 and x of t2 are the two sample random variables from a single random process. So mathematically, the auto-covariance of the random process x of t is denoted as cxx of t1 comma t2. The auto-covariance function of the random process x of t is defined as the covariance of the random variables x of t1 and x of t2. And it is given by mathematically c suffix x of t1 comma t2 is equal expectation of x of t1 minus expectation of x of t1 into x of t2 minus expectation of x of t2. So this is the definition of auto-covariance function of the random process x of t. So now here on RHS side, this within the bracket term, multiplying this term and this term, we get four terms. So that four terms are x of t1 into x of t2 minus x of t1 into expectation of x of t2 minus expectation of x of t1 into x of t2 minus into minus plus expectation of x of t1 into expectation of x of t2. And after that, on RHS side, applying expectation property. So expectation of sum of random variables is equal to sum of their individual expectation. So that is expectation of xy is equal to expectation of x into expectation of x plus y is equal to expectation of x plus expectation of y. And one of the property of the expectation of x of t1 is expectation of x of t1. So therefore, using that property, the RHS term is expectation of x of t1 into x of t2 minus expectation of x of t1 into expectation of x of t2 minus expectation of x of t1 into expectation of x of t2 plus expectation of x of t1 into expectation of x of t2. So now here on RHS side, one term minus expectation of x of t1, expectation of x of t2 plus expectation of x of t1, expectation of x of t2 is the cancel. And the remaining RHS term is expectation of x of t1, x of t2 minus expectation of x of t1 into expectation of x of t2. So the first term of the RHS, on RHS side, the first term is autocorrelation function of the random process x of t, that is Rxx of t1 comma t2. So therefore Cxx of t1 comma t2 is equal, this is definition of the autocorrelation function of the random process, that is Rxx of t1 comma t2 minus, so expectation of x of t1 is also denoted as m suffix x of t1 and expectation of x of t2 is also denoted as m suffix x of t2. The value of the autocovariance of the two random variables observed at the same time instance. At the same time instance means that is time t1 is equal to t2, t2 is equal to t. Okay, applying this condition into above expression, okay, observed at the same time, the autocovariance function of the random process is Cxx of t comma t, t1 is equal to t and t2 is equal to t. So which is equal to Rxx of t comma t minus mx of t into mx of t. So Rxx of t. So the from the one of the property of the autocorrelation function of the random process, the autocorrelation function of the two random variables observed at the same time instant, that is Rxx of t comma t is the mean square value of the random process, that is expectation of x square of t. And the second term is mx of t into mx of t whole square. So therefore, Cxx of t comma t is equal expectation of x square of t minus mx of t whole square. So the RHS term of this equation is the variance of the random process x of t, that is variance of x of t. If the random process x of t is at least Whiteson stationary random process, then Cxx of tau is equal Rxx of tau minus expectation of x of t whole square. This is the concept of autocovariance function of the random process x of t definition derivation. And next, correlation, autocorrelation coefficient. Okay, from the above expression, substitute tau is equal to 0 in this equation. Substitute tau is equal to 0. Tau is equal to 0. We get Cxx of 0 is equal Rxx of 0 minus expectation of x of t whole square. From one of the property of autocorrelation function of the random process, the value of Rxx of 0 is expectation of x square of t. So therefore, Cxx of 0 is equal expectation of x square of t minus expectation of x of t whole square. The RHS term of this equation is variance of the random process, that is variance of x of t. At tau is equal to 0, Cxx of 0 is variance of the random process x of t. The autocorrelation coefficient of the random process x of t is defined as rho xx of t1 comma t2 is equal Cxx of t1 comma t2 divided by square root of Cxx of t1 comma t1 Cxx of t2 comma t2 or rho suffix xx of t comma t plus tau is equal. So T1 is equal to T and T2 is equal to T plus tau. Okay, this equation is also written as rho xx of T comma T plus tau is equal Cxx of T comma T plus tau divided by square root of Cxx of T comma T Cxx of T plus tau comma T plus tau. So in this equation, substitute tau is equal to 0, we get the autocorrelation coefficient value is 1. So this is the concept of auto-covariance function of the random process x of t. Next we are going to discuss about cross-covariance function of the random process. The cross-covariance function of the random process x of t and y of t is denoted as c suffix xy of t1 comma t2. The cross-covariance function of two random process x of t and y of t is defined as the covariance of the random variables x of t1 and y of t2. So mathematically, and it is given by Cxy of t1 comma t2 is equal expectation of x of t1 minus expectation of x of t1 into y of t2 minus expectation of y of t2. So on RHS side, multiplying this within the bracket two terms, we have four terms. So that are x of t1 into y of t2 minus x of t1 into expectation of y of t2 minus expectation of x of t1 into y of t2 minus into minus plus expectation of x of t1 into expectation of y of t2. So using properties of expectation, applying the expectation into each term on RHS side, we get Cxy of t1 comma t2 is equal expectation of x of t1 y of t2 minus expectation of x of t1 expectation of y of t2 minus expectation of x of t1 expectation of y of t2 plus expectation of x of t1 expectation of y of t2. So now here on RHS side, one minus term, one plus term is the cancelled, and the remaining RHS term is expectation of x of t1 y of t2 minus expectation of x of t1 into expectation of y of t2. So on RHS side, the first term is cross correlation function of the random process x of t and y of t, that is rxy of t1 comma t2. Therefore Cxy of t1 comma t2 is equal rxy of t1 comma t2. So this expectation of x of t1 is also written as m suffix x of t1. Expectation of y of t2 is also written as m suffix y of t2. And substitute, consider t1 is equal to t and t2 is equal to t1 plus tau. So t1 is equal to t, then t2 is equal to t plus tau. So therefore Cxy of t comma t plus tau is equal rxy of t comma t plus tau minus mx of t my of t plus tau. Since random process y of t is stationary random process, so expectation of y of t plus tau is expectation of y of t. Expectation of y of t plus tau is equal expectation of y of t. So therefore, applying this condition into this equation, we get Cxy of tau is equal rxy of tau minus mx of t my of t. This equation indicates that the random process are at least jointly Wheatstone stationary random process. The cross covariance function is not a function of absolute time t. If two random process x of t and y of t are uncorrelated random process, then the cross covariance function of the two random process is 0. That is Cxy of tau is equal to 0. Cxy of tau is equal to 0, then the cross covariance function of the random process x of t and y of t, we get the condition for independent random process, that is rxy of t comma t plus tau is equal expectation of x of t into expectation of y of t plus tau. Therefore, The independent random process are also uncorrelated. If Cxy of tau is equal to 0, the uh, cross correlation function of the random process is product of their individual expectation. That means random process x of t and y of t are uncorrelated random process. The cross correlation coefficient of the random process x of t and y of t is given by rho suffix xy of t1 comma t2 is equal cxy of t1 comma t2 divided by square root of cxx of t1 comma t1 cyy of t2 comma t2. In this equation, substitute t1 is equal to t and t2 is equal to t plus tau. Therefore, rho xy of t comma t plus tau is equal cxy of t comma t plus tau divided by square root of cxx of t comma t cyy of t plus tau comma t plus tau. In the above expression, substitute tau is equal to 0, rho xy of 0 is equal cxy of 0 divided by sigma x into sigma y. So this is the concept of cross covariance function of the random process